Okay, hello everyone. My name is Howard Lo, and my team member is Hubert and Chang. Our topic is travel to animal world with cycle consistent adversarial networks. And here's our outline. We'll first talk about our project motivations and mention a little bit about CycleGAN, and then introduce our data set and our methods, and show a bunch of interesting results in our experiment parts. And this is our project motivation. My teammates and I are quite fascinated by what GANs can achieve. And we are also enemy lovers. And inspired by this recent Facebook VR demo, we thought that wouldn't it be very entertaining if we transform our faces to animal faces like this demo. So traditionally, if we want to generate the image from domain A to domain B, we will apply conditional GANs like this figure. And conditional GAN can generate images from segmented images to street scenes, and from day images to night images, or in our case, we want to generate animal face from human face. But unfortunately, the training framework of traditional conditional GANs needs paired training data, where each image from domain A needs to be aligned with the other image from domain B. So in our case, it's very costly to have aligned human face and animal face images. So until recently, the latest advance of GANs has introduced an unsupervised way to learn the mappings from different domains, which cannot be achieved by CycleGAN. So our work is based on the CycleGAN training framework, and we modify it by applying different techniques. So for those who are not familiar with CycleGAN, I think I briefly explain how the CycleGAN works. So basically, there are two GANs in CycleGAN training framework. One is for learning the images from domain A to domain B, and the other one is learning the images from domain B to domain A. And here in our illustration, we'll explain the training process from translating from domain A to domain B, which is the human face from animal face. We have the true human face as input, and the generator from domain A to domain B will generate a fake animal face. Then we can use the generator from domain B to domain A to generate back to the fake animal face. Now we have the true human face and fake human face. We can use L1 as a cycle consistency constraint. And this can help our models to make sure the source content and the generic content can be the same. And the other way is the same. So also note that the original CycleGAN uses LS-GAN loss. And in our approach, we modify the LS-GAN loss with FisherGAN loss, which is the new loss introduced in NIPS 2007. And 2017, yeah. And we also tried spectral normalization, which is currently under review in ICARE 2018. And it can make our model become more stable. So here's our data set. For the realistic human facial images, we select the benchmark data set called Celebrity A, which contains about 200,000 images. And the resolution is 170 by 170. For the animal images, we collect about 3.5 thousand images, and the resolution is 2.500 by 300. In the preprocessing step, for human face images, we first apply face recognition and perform center crop, and resize it to 256 by 256. And for animal images, since the human face recognition algorithm failed to recognize the animal face, so we basically apply center crop on animal images. The problems of the animal images, even if we perform the cropping on our element images, there are some weird cases in our data, like the figure shown here. We have 3 eye character and field cropping images, character in weird accessories, and there are multiple characters in one images. Okay, and here's our experiment outline. We totally performed 7 different experiments with physics and 2 GPU cards, and we divide them basically 2 sections on the different phase of CycleGAN model. For experiment 1 to 4, we based on the CycleGAN with the LS GAN loss, which is the original version, and tested by accumulating the different techniques. And for experiment 5 to, sorry for the number, for the experiment for the 5 to 7, we based on the CycleGAN with FisherGAN loss. And we also tested it by accumulating some different techniques. And the highlighted experiment with the red color is the best model corresponding to their base CycleGAN model. So we'll show their results one by one. Okay, the first is CycleGAN and just trained on non-cropped images. The result is quite bad, and we cannot find any phase global coherence on the generated images. And you can note that the eyes part is quite weird. And the second experiment, we trained CycleGAN on cropped image. We found that the model performs better than the previous one, which the generated phase contains less weird parts. The number under the images indicates the model complexity. For the experiment 3, we add spectral normalization and get slightly better quality. And you can see the hair is quite similar to the generated element here. And for experiment 4, we add noisy label training techniques, and we found that the coverage space becomes faster, and the generated results are generally getting better. Especially, we can observe the improvements from the highlighted part of the images. From the top left example, we can see that our model can successfully generate a curly hair. For the bottom left example, the element phase seems to be very complete. And the bottom right example, the model also noticed the head in the image. From experiment 5, we now show the result generated by CycleGAN with FisherGAN loss. So this is the results generated by CycleGAN loss with FisherGAN loss trained on cropped image. And the result seems better than the previous one. And here are the results after adding spectral normalization. And finally, we also resize our image size to 128 by 128. And we found that the overall quality is better than the original size. And the model here performs the best among the other experiments. For this size, this result is from training data. And same settings as previous slides, the result shown here is from testing data. Note that our element data is mostly consists of girls. So yeah, our generated element characters is mostly like girls. Even the human is men. Yeah. Yeah, and also we put our reviewers image as our testing thing. Yeah. Professor this result shows is much it's nice, yeah. Okay, and here is our interesting case. We also put some outliers that is not human face. Like I think the most interesting example is the watermelon shown at top right. The model might think that the texture of the watermelon is similar to the hair of the anime characters. So the model also generates an accessory for the watermelon and also the curly hair. Yeah. Thanks for your listening.
So I have a quick comment. So this is very interesting, and I found that when we transform the real image from the enemy faces, usually they are not look quite alike. For example, the color of the hair will is changed. I think one reason is the enemy faces are very different from the real faces. So one way to solve is probably use another set of real face image, because your real face image are from select A. And they do not have weird color hair. So probably you can crop the image from, for example, cosplay for, so probably you can get better results.
All right, interesting work. Let's thank the speaker.